In this video, we'll take a look at some of the ideas that motivated calculus. We'll start with the tangent problem. Basically, the tangent problem is the problem of answering the question, what exactly is a tangent line? Our first try might just simply be that a tangent line is a line that intersects the curve exactly once. The problem with this is that it is possible for a line to intersect a curve and intersect it only once, but not be what we would call a tangent. It might pass through from one side to the other. Here's a parabola, and you can see that there's a line passing through that intersects it only once, but we wouldn't think of that as a tangent line. Let's make a second try. Let's say that a tangent line touches the curve but does not pass through the curve. Does this idea work? Well, we haven't given mathematical definitions for touching and passing through, but we have an intuitive understanding of what these ideas mean. And this seems to work in the simple cases. It works in the case of a parabola, and it works in the case of a circle. However, it doesn't necessarily work in other cases. This first graph that you see here, it has a horizontal tangent line at the point -1, 4. That should be an at. So it has a horizontal tangent line at the point -1, 4. But that line does intersect the curve at approximately x equals 1.6. This line is what we would call a tangent line, and it almost satisfies our definition, but not quite, because it does pass through the curve. Of course, it passes through the curve far away, and so we don't want to let that bother us, but we just need to find another definition where we can have it touching at one point and passing through at another. This curve that you see here, this is the graph of y equals x cubed, and it has a horizontal tangent line that passes through the curve at the origin, at the point 0, 0. That's the x-axis. Now, why do we want that to be a tangent line? The tangent line is the best linear approximation to the curve at the point of tangency, and y equals x cubed is really flat at the origin. So we want this to be a tangent line, even though it quite definitely just passes through the curve. But it sort of just seems to sit there at the origin, and that's why we want this to be a horizontal tangent line to a curve where that curve looks really flat. So how do we determine the equation of a line? We need 2 points. We need 2 points because 2 points determine a line. When we want to find the equation of a tangent line, we have a problem. And that problem is that we have only 1 point, which is the point of tangency. So even in the simple cases of a circle and a parabola, we don't have an easy way of finding a second point on the tangent line. So this brings us to our third try. Let's approximate the tangent line with what we call a secant line. A secant line is a line that crosses through the curve twice. So we'll start by picking a point a, f of a on the graph. We want to determine the equation of the tangent line at this point. So we want to determine the equation of this dashed line here. Notice that the x-coordinate is a, and the y-coordinate is f at a. So that's why this point is a, f at a. So a secant line passes through 2 points on the graph. So let's pick another point. So here's our point a, f at a, right here, a, f at a. And let's pick another point right here. This point has coordinates b, f at b. So we can find the equation of the line that passes through these 2 points, which we've written in, or that we've drawn in blue. So we can find the equation of that line because we have 2 points. They're the 2 points on the graph where the secant line passes through the graph. So here's our graph of our function, y equals f at x, and through this graph we draw this blue line, and it intersects the graph twice. So we have 2 points of intersection, and using those 2 points we can write down the equation of the line. So the equation of the line is y equals m, where m is the slope, times x minus a plus f at a. So really what we're doing here is we're looking at the equation y minus the y value is equal to the slope times x minus the x value. And then we just added f at a to both sides. That's how we got here. But importantly, we can now figure out what the slope is. Notice that in this equation, we only used one point. We used the point with x-coordinate a and y-coordinate f at a. But we do need another point, and that's what gives us the slope. The slope is the difference of the y's divided by the difference of the x's. So it's f of b minus f of a divided by b minus a. So for any 2 points on the curve, we can draw a secant line through those 2 points, and we can very easily determine the equation of the tangent line, because it's easy to determine the slope if you have 2 points. Now, the slope of the line that we picked here doesn't appear to be the same as the slope of the tangent line. The 2 lines intersect, but when we say that 2 lines are close, we don't necessarily mean that they intersect each other. We mean that they have approximately the same slope, because we want all of the points on one to be approximately the same as the points on the other. So we want the slopes to be very similar. In this case, the slope might not be too close to the slope of the tangent line, but maybe that's because we picked a point that was just simply too far away from our original point. If you pick a point that's much closer on the graph, then the slope of the secant line is closer to the slope of the tangent line. So this is the same graph of the same function that we saw before, and this dot right here, that's our original point with coordinates a, comma, f at a. This blue dot right here, this is the point with coordinates b, comma, f of b. This is the one that we were looking at before. And so this blue secant line is the one from the previous slide. Well, if we choose a point that has x value closer to a, for example, this point here, and then we draw a secant line through the original dot and this orange dot, you can see that we get a line which is closer to the dashed tangent line. And then this red dot is even closer still, because the x value, the x coordinate, is closer to a. And that gives us even a closer secant line. And when I say closer, I mean a secant line that is closer to the tangent line. Let's zoom in on this so we can get a better look. So here we are. This is zoomed in. We've added some numbers here just to give it a sense of scale. But you can see that these are the same lines as before. You can see the same points that were on here as before. But now you just get a better look at the lines. This blue line is our first secant line. And then as the point gets closer on the curve, that is, as our x-coordinate gets closer to a, so our x-coordinates are moving to the left here. So as our x-coordinates gets closer to a, you draw these secant lines which look more and more like the tangent line. So this red secant line is a lot closer to the tangent line than the blue one was. Now let's zoom in really, really close. So we can see our point a, comma, f at a right here. Now what I want to do is I want to pick a point very close to that, arbitrarily close, in fact. And the way that I do that is I pick some close point. Now I'm representing that by choosing an x value, which I'm calling a plus h. So here's our a. The x-axis is somewhere down here, by the way, because we're zoomed in on this part of the curve. So the x-axis is way down here, the y-axis is way over here. So we have some x value a, and we're just going to increment it by a little bit. So h is a really small number, so this is a really tiny number. So we have a here, that's our original x value, and then we're going to increment it by some small amount. So that has a corresponding y value, which is f at a plus h. Now our function was decreasing in this picture, so that's why even though a plus h is to the right, f at a plus h is below f at a, it's smaller. That's because in this picture I imagined that h was a positive number, but h can be negative. So we might want to choose a point to the left of x equals a. So we might want a point over here, in which case we allow h to be negative. So h can be positive or negative. So now we can compute the slope of this secant line. Since a plus h is really close to a, these two lines are going to be very close to each other. This secant line is very close to the tangent line. So I can compute the slope of the secant line. So we'll call that m sub h. The h is just here because we're showing that there's a dependence on this h here. So it's the difference of the y values divided by the difference of the x values. So the y values are f at a plus h minus f at a. It's the difference of these two. And we're dividing that by the difference of the x values, which are right here, a plus h minus a. Now, of course, you get a little bit of simplification going on here. That a cancels with that a, and you just end up with an h in the denominator. This is our rise over run. We're rising by the difference between the y values, and we're running by the difference between the x values. But the difference between the x values is just h. This is just h. So our slope for our secant line, which we're calling m sub h, is f at a plus h minus f at a divided by h. So if h is really small, then this slope closely approximates the slope m of the tangent line. The smaller h becomes, the better the approximation. And this gives us the definition for the tangent line that we want. Or rather, it gives us the definition for the slope of the tangent line. We define the slope of the tangent line at this point, a comma f at a, to be the value of the following limit, if it exists. So we look at the slope of the secant line, which is f at a plus h minus f at a, and divide that by h. This is the slope of the secant line. And if h is really small, then it's close to the slope of the tangent line. So what we're going to do is we're going to compute the limit as h goes to 0. So this limiting value will be the slope of our tangent line. Since the slope of the secant line gets closer and closer and closer to the slope of the tangent line, we just imagine that the slope of the tangent line is the limiting value. It's the thing that it's getting closer and closer and closer to. This is actually how we define the slope of the tangent line, and in essence, that's how we're defining the tangent line. We're defining the tangent line to be the line that passes through this point, a comma f at a, with the slope given by this limit. That's how we're defining the tangent line. And there is a tangent line provided this limit exists. It might be that it doesn't exist, in which case there won't be a tangent line. Let's look at an example. Find the equation of the tangent line to y equals 2 minus 1/2 x squared when x equals 1. So this is the graph that we're looking at here. Y equals 2 minus 1/2 x squared when x equals 1. So here's 1 right here, and you can see that the point when x that has x coordinate 1 has y coordinate 3/2. And we can just compute that directly. X is equal to 1, so y, you know that y is equal to 2 minus 1/2 x squared. So if x is equal to 1, you just replace this x with 1. That's what we've done here. 2 minus 1/2 x squared. So of course 1 squared is 1, so 2 minus 1/2 is 1.5 or 3/2. So that gives us the point. You need two things to write down the equation of a line. You need a point, which is the point of tangency, and you need the slope. Now we know how to find the slope of the tangent line. Let f at x equal 2 minus 1/2 x squared. This formula here comes from the equation of the curve. remember that the curve was y equals 2 minus 1 half x squared. So this function has graph given by this parabola, y equals 2 minus 1 half x squared. That's the graph of this function. So the point on the tangent line that we're interested in is the point with x-coordinate 1 and y-coordinate f at 1. 1 comma f at 1, which of course is 1 comma 3 halves. So the slope of the tangent line at x equals 1 is given by this limit. M equals the limit as h goes to 0 of this difference of the y's divided by the difference of the x's. So that's f at 1 plus h minus f at 1 divided by h. Now we know what f of 1 is. F of 1 is 3 halves. So we've already determined that f of 1 is 3 halves. Well, we need to determine what f at 1 plus h is. So let's compute that. So f at 1 plus h is 2 minus 1 half times the input value, which is 1 plus h, quantity squared. So our formula for f at x is just the input. So whatever the input is, you look at 2 minus 1 half and then the input squared. So in this case, our input is 1 plus h. So it's 2 minus 1 half times the input squared. So let's just simplify this. This is going to be equal to 2 minus 1 half times 1 plus 2h plus h quantity squared, or just h squared. So what is that going to be? That's 2 minus 1 half minus h minus 1 half h squared. Notice that we have a minus 1 half, so that's why all of these terms are minus because of that minus. 1 half times 1 is 1 half. Minus 1 half times 2h, the 1 half cancels with the 2, and you just have minus h. And then we have minus 1 half times h squared. That's where this term comes from, minus 1 half h squared. You can simplify this just a little bit. 2 minus 1 half is 3 halves. So now we can take this and plug it right into here. So we know what f of 1 is. We've already established that. Now, f of 1 plus h, that's the thing that we just computed right here. But let's use that 3 halves. Okay, so let's just plug it in. So we're going to have 3 halves minus h minus 1 half h squared. And from that, we're going to subtract f of 1, which is 3 halves. And all of this is divided by h. Now, the first thing that you might notice is that that 3 halves will cancel with that 3 halves. So let's just go 3 halves cancels with 3 halves. And now we're just left with minus h minus 1 half h squared divided by h. Now everything here has an h in it. So what we can do is we can say that m sub h is equal to, we can factor out an h. So we'll have h times minus 1 minus 1 half h, and all of this is divided by h. And let me just fix this h. It looked a little bit more like a k. That's supposed to be an h. Now, this h in the numerator will cancel with that h in the denominator, and we're just left with minus 1 minus 1 half h. So this is the slope of the secant line that passes through these 2 points, the point 1 comma 3 halves and a point that's just a little bit of a distance away. So the slope of the tangent line is going to be what we're calling m. It's the limit as h goes to 0 of the slope of this secant line, which is right here. It's circled here. So this is going to be the limit as h goes to 0. That just means h is really small. And we've just computed this. It's minus 1 minus 1 half h. So the question is, what happens to this value as h gets really small, as h goes to 0? Well, this number right here is going to 0. So this minus 1 half h, this quantity right here, this is going to go to 0. h is getting really, really, really small. So this h value is getting really, really, really close to 0. So if you take something which is really close to 0 and halve it, it's still going to be really, really, really close to 0. So this value is getting really close to -1, -0. So it's getting close to -1. So that tells me that the slope of the tangent line is -1. So the equation of the tangent line is going to be y minus the y value, which is f of 1, equals m, which is the slope, times x minus the x value, which is 1. So x is 1 here. And f of 1 is 3/2. Remember, we'd already determined that. So 3/2, that's our f of 1. So y minus 3/2 is equal to the slope, which we've just determined is -1, times x minus 1. So that's the equation of our tangent line. Of course, we can simplify this. Y minus 3/2 equals minus x plus 1. And let's just add 3/2 to both sides. Y equals minus x plus 1 plus 3/2 is 5/2. And that's the equation of our tangent line in slope-intercept form. Let's do another example. For this example, we want to show that the tangent line to y equals x cubed at the origin is in fact horizontal. We mentioned earlier that we expect that it will be, because the graph is really flat here. So we expect that the tangent line should be horizontal, and we want to show that that is the case. So first we need to identify the function. Well, the function in this case is f at x equals x cubed. And we want to find the slope of the tangent line to this function at the point 0, 0. So what we need to do is we need to compute the slope, m equals the limit as h goes to 0 of f at 0 plus h minus f at 0 divided by h. Our goal is to show that the tangent line is horizontal, so we want to show that the slope is 0. That's our objective here. So f at 0 plus h, this thing, that's 0 plus h is just h. So we have that m is equal to the limit as h goes to 0 of f at h minus f at 0 over h. So we can compute these things. M is equal to the limit as h goes to 0 of f at h. But f at x is x cubed, so we're just going to replace x with h. So it's going to be h cubed minus 0 cubed, which of course is just 0, divided by h. So this is going to be the limit as h goes to 0 of h cubed divided by h, which is the limit as h goes to 0 of h squared. As h goes to 0, h squared is also going to 0. So that means m is 0. So the slope of the tangent line at the point 0, 0 is m equals 0. And if the slope is 0, that means that the line is horizontal. Let's look at a more complicated example. Show that the tangent line to x squared plus y squared equals 1 at the point where the x coordinate is the square root of 2 over 2 and the y coordinate is square root of 2 over 2 has slope -1. So we're looking at this circle here. This circle has equation x squared plus y squared equals 1. It's the unit circle. And this point right here has coordinates square root of 2 over 2, comma, square root of 2 over 2. Incidentally, this is the point on the unit circle where sine and cosine have argument pi over 4. So it's certainly believable that the slope here is -1. We certainly don't find that surprising because of the symmetry of the circle. But we want to verify that it is in fact -1. We don't want to just say it looks like it's -1 from the picture. We want to show that it actually is. So how are we going to do this? Well, we want to find the slope of the tangent line when x is equal to the square root of 2 over 2. So this is going to be m, is going to be the slope of our tangent line, which is the limit as h goes to 0 of f at the x value plus h minus f at the x value divided by h. Well, now what is this f thing that suddenly we've introduced? F is some function, and in this case, f at x is the square root of 1 minus x squared. Where does that come from? That comes from the equation of the circle. X squared plus y squared is equal to 1. So basically you just solve for y. So y squared is 1 minus x squared, and then we compute the square root. So if y squared is 1 minus x squared, then y is plus or minus the square root of 1 minus x squared. Notice that we have a plus or minus here. Now what we want is the plus. So the positive square root gives us the top half of the circle. Now remember, what we're looking at here is y equals, it's giving us the y coordinate. So if you specify an x value, we want to look at the positive y values. So we're interested in the top of the circle here. So the top of this circle has equation y equals the positive square root of 1 minus x squared. That's the top half. The bottom half is the negative square root, 1 minus x squared. That's the bottom half. We're interested in the top half because the point we're looking at is on the top half of the circle. So we want to select the top half, the plus. And that's where this formula for f comes from. So we want to compute the slope of the tangent line to this f, the curve, which is the graph of this f, at the point where x is equal to the square root of 2 over 2. So that's what we're going to do. So the computations here are a little bit more involved, so I've typed everything out in advance. We want to compute the limit as h goes to 0 of the difference of the y's over the difference of the x's. So this is the slope of the secant line. F at the square root of 2 over 2 plus h minus f at the square root of 2 over 2. We compute that difference and divide it by h. So remember what f is. Let's just scroll back briefly. F at x is the square root of 1 minus x squared. So whatever the input is, we look at the square root of 1 minus the input squared. So that's what we have here. F evaluated at some input. So that's this portion right here. So let's just highlight it. This goes to here. Or perhaps more specifically, what we want to highlight is just the input, which is right here. And that shows up right here. And altogether, it's going to be in that underneath that radical. So we look at the input, and it returns, if we look at our function, the square root of 1 minus the input squared. So it's the square root of 1 minus the input squared. So the input is all of this, the square root of 2 over 2 plus h. Now that's the first occurrence of f. We have another occurrence of f here, f at the square root of 2 over 2. So what is that going to be? Well, that's the square root of 2 over 2. This is just the y value. So if we go back on our graph, we can see that we're looking at this point. And this point, where our angle is pi over 4, that's when the x and y coordinate are the same. So x is the square root of 2 over 2, and y is also the square root of 2 over 2. So this number right here, this is f at the square root of 2 over 2. So this is the place where the input and the output are the same. So that's why we just have f of the square root of 2 over 2 is equal to the square root of 2 over 2, because the input and the output are the same for this one. So this one is the same as this one. Okay, well now it's just a matter of simplifying. So the thing we need to simplify is what's underneath this radical. So let's start by the quantity that we're squaring. So the square root of 2 over 2 quantity squared, that's going to give us 2 over 4. Square the numerator, square the denominator, 2 over 4. Plus 2 times the first times the second. So it's 2 times the square root of 2 over 2 times h. And then we add in h squared. So we can simplify this. 2 over 4 is 1/2. And then here we have a 2, and we're dividing by 2. So let's just cancel those, that 2 and that 2, and then we're just left with the square root of 2 times h. And then we haven't done anything to this h squared. Okay, so we can simplify it just a little bit more. 1 minus 1/2 is 1/2. Then we have minus the square root of 2 times h, and then we distribute this minus sign through, it's minus h squared. And we haven't done anything to the terms outside of the radical. Okay, now how do we simplify all of this? Well, there's a little bit of a trick to getting rid of radicals, and that means you multiply them by what we call their conjugate. So you multiply it by the same thing, so it's 1/2 minus the square root of 2h minus h squared, but then you put a plus here, square root of 2 over 2. So the only difference between this numerator and what I'm multiplying by is I've changed the minus sign to a plus. Now why would I do that? I have some quantity a minus another quantity b, and then I'm multiplying it by the same quantity a plus b. So this is going to give me the difference of squares. So the squares will get rid of my radicals here. Now, of course, if I put it in the numerator, I have to put it in the denominator as well. So it's the square root of 1/2 minus the square root of 2h minus h squared plus the square root of 2 over 2. So I'm going to multiply this by all of that. And again, I'm just using the idea that I'm looking at the difference of squares. So if I just highlight this one, this is the same as this term here. And then we have this term right here is the same as this term there. So we're looking at a minus b times a plus b, and this gives us the difference of squares. So that's what I'm going to make use of. So let's go to the next slide and we'll see that. So here I've just written down exactly the same thing that's on the previous slide here. I've just typed it up so it looks a little bit nicer, but this is our b. This is our b term, b, which is going to give us a b squared. So that's this term right here. And then we have, this is our a term here, including the radical. So a, and then it's a squared. So you can see that we have a quantity squared. The whole reason we're doing this is that when you square the square root, the radical goes away, and then you're left with this term right here. Now notice the denominator, we haven't really done anything with it. We just have h times all of this in the denominator. We haven't done anything to the denominator. That'll come later. So we simplify the numerator because we have the square root, but then we're squaring it, so the radical goes away. We just have 1/2 minus the square root of 2h minus h squared. And then let's square this term. So the square root of 2 squared is 2, and 2 squared is 4. Okay, now 2/4 is 1/2. So we have 1/2 minus another 1/2. These two terms will disappear. And then we're just left with minus square root of 2h minus h squared. Now the denominator, again, we haven't done anything here. But notice that there is an h in both terms of the numerator, so we can factor out that h. And that's what we do here. Just factor out the h. And why do we factor out the h? Well, now we have an h in the numerator and an h in the denominator, and those will cancel out. H is getting close to 0, but it's not 0. It's some number which is not 0, but it's really close to 0. So these two numbers, h and h, will cancel out. And now we have the limit as h goes to 0 of the numerator, which is minus square root of 2 minus h. And the denominator is still pretty complicated. We've gotten rid of that little h. But notice all of the h's that appear here. There's an h there, there's an h there, and we have an h in the numerator. But this limit as h goes to 0 means that h is getting really, really, really small. So whatever this value is, it's getting really, really close to a number where h is 0. So we just plug in h equals 0. And now everything that has a 0 goes away, and you're just left with this term, minus the square root of 2 divided by the square root of 1/2 plus the square root of 2 over 2. Now the square root of 1/2, this term, the square root of 1/2, that's the same thing as the square root of 2 over 2. You just look at the square root of 1/2 is 1 over the square root of 2, and then just multiply by the square root of 2 over the square root of 2 to rationalize the denominator, and you'll have the square root of 2 over 2. So those are the same. So then we have the square root of 2 over 2 plus the square root of 2 over 2. That's half of the square root of 2 plus another half of the square root of 2 gives us a whole square root of 2. But we have a negative square root of 2 in the numerator, so those will cancel and just leave you with the minus 1. So yes, in fact, the slope of the tangent line at this particular point is minus 1. Now you might wonder why we didn't just plug in h equals 0 to begin with. If we scroll back way to the beginning, way back to the beginning, way up here let's say, if you were to plug in h equals 0 here, you just end up with a 0 in the numerator and a 0 in the denominator, which is undefined. So if you just get rid of that h, you'll have 1 minus the square root of 2 over 2 quantity squared, which is going to give you 1/2. And then so you'll have 1 minus 1/2, but then you have the square root of that. And then you're here, this is also the square root of 1/2 as we just saw. So you'll just end up with 0 over 0. And that's undefined. And in fact, you'll have 0 over 0 at each step of the way right up until you canceled your factor of h. And in fact, that's the whole reason we played this algebraic game here. That's the reason that we multiplied by this term. We multiplied by this term to get all of these h's out of the radical, because ultimately what we wanted to do is we wanted to have a factor of h in the numerator. We already had a factor of h in the denominator, but we wanted to figure out where there was a factor of h in the numerator. And we knew that there had to be. There had to be a factor of h in the numerator because way back here, if you try plugging in h equals 0, you get 0. So that means buried in here somewhere is a factor of h, and we just had to find it. Now, we had to play this algebraic game to do so, but eventually we found that factor of h right there. We factored it out. There was a factor in the numerator, a factor in the denominator. Those simplified, and then we didn't have a factor of h in the numerator and a factor of h in the denominator. So we got rid of the thing that was giving us 0 over 0. This h was giving us 0 in the numerator. This h was giving us 0 in the denominator. But then we factored them out, and they canceled with each other, and now we got rid of that 0 over 0. So at that point, you could just start plugging in h equals 0, everything simplifies, and you just end up with the slope of your tangent line being minus 1. This brings us to the second problem that motivates calculus, or the development of calculus, which is the velocity problem. So what is the velocity problem? Well, it's a question. That question is, what is instantaneous velocity? We have an intuitive idea of what we mean by instantaneous velocity. For example, a car's speedometer gives the car's speed at any instant of time. We call it the instantaneous speed. But have you ever wondered about how that was computed? What do we even mean by speed? Well, if we travel at a constant speed v for t seconds, then we can determine what v is by writing it as d divided by t, where d is the distance traveled during that time. So the distance traveled per time gives us the velocity. But speed in a car changes from moment to moment, so we can't say that speed is constant for very long. But if we take a very short interval of time, delta t, then we can say speed is approximately constant over that interval. Let's define a function, a distance function. Let s at t be the distance traveled after t seconds. Then s at b minus s at a is the distance traveled over a time interval from a to b. The average speed over this interval of time from a to b is given by this ratio, s at b minus s at a divided by b minus a. This is the distance traveled divided by the amount of time you've been traveling. To find the instantaneous speed at a time a, look at a very small interval of time near a. So let's say we start at a, and then we just increment a just a small amount, so a plus h, where h is thought of as a very small number. And now we compute the average speed. So the speed, which we're calling v sub h, is equal to s evaluated at a plus h minus s at a. This is the total distance traveled between time a and time a plus h, where again h is just some small number. So the numerator here is the distance traveled over a very small amount of time. The denominator is that small amount of time. The difference between these two time values, a plus h minus a, is just going to be h. So if the interval is small, that is, if h is really small, then v sub h is approximately the instantaneous speed. So this should look a little bit familiar. Well, we're going to define the instantaneous velocity in this way. So if s at t is the distance traveled after t seconds, then we define the instantaneous speed at t equals a to be the speed at a is equal to the limit as h approaches 0 of this ratio, s at a plus h minus s at a, the total distance traveled over this small interval, divided by h, which is the amount of time that's passed. We want this to be really small, so we consider the limit as h goes to 0. But this instantaneous speed is found in the same way as the slope of a tangent line. And this is a very important idea. If s at t is the distance traveled after t seconds, then the instantaneous speed at time t equals a is the same as the slope of the tangent line to y equals s at t at the point a comma s at a. So there's a relationship here between the instantaneous speed and the slope of a tangent line. We've been talking about speed, but sometimes we're not interested in speed so much as velocity. Instead of having s at t be the distance traveled, suppose it's the distance away from a fixed point. Then sb minus sa isn't the distance traveled anymore. Now it's the displacement over the interval from a to b. So it's not necessarily the distance traveled. In this case, this quantity v at a is no longer the instantaneous speed. Now it's called the instantaneous velocity. So let's take a quick example so we understand what's going on here. Suppose a stone is thrown upward, and s at t is the distance above the ground. So s at t is no longer the distance that the stone has traveled. Now it's the height relative to the ground. So s at t is the distance above the ground after t seconds. If the rock is in the air for 2 seconds, that means that it's on the ground after 2 seconds. So s at 2 minus s at 0 is 0. The displacement is 0. The rock ends where it starts. So even though some distance has been traveled, there is no displacement because it went up and then it came down and it ended in the place that it started. That means that there is no displacement. We've defined two things, the slope of a tangent line and the instantaneous velocity or instantaneous speed. In both cases, we define them in terms of a limit. In the case of a tangent line, it was the limit of the slope of secant lines. In the case of the instantaneous speed or instantaneous velocity, it was the limit of average velocities. So this quantity that we're looking at has a name. It's called the difference quotient. Given a function f, which is a function of x, then the expression f at a plus h minus f at a divided by h is called the difference quotient. When you're looking at a curve, this gives you the slope of a secant line. When you're looking at velocity, this gives you the average velocity over an interval of time. And the limit of this difference quotient as h gets closer and closer to 0 is either the slope of the tangent line or it's the instantaneous velocity. And we actually see now that the instantaneous velocity is the slope of a certain tangent line. This quantity, the difference quotient, appears again and again, and this is really what we're looking at. And then we're computing the limit of these difference quotients as h goes to 0.